here we go. I'm going to put some piece of tape on the bicycle tire. Okay, here we go. All right, this is gonna. I'm not promising you, but I'm gonna tell you this is probably gonna be the last of these exciting audio-visual demonstrations here. I'm just gonna go back to our place in the universe over here and go around as the orbit of the moon one last time. Okay, remember this chart over here was the height of this thing above the center line as you go for each different degrees. See how it goes up, goes down, and back up again. All right, but I'm now going to show you what this is all about. The idea is that we had the guy going around with the spring in a nice circle. That's the Mahalik Soy of the moon. Put it a little bit off center from where the observer is, and then it looks like the moon slows down when it's farther away because the guy is watching it not from the center, even though it's still going at the same speed around there. That does not account for enough of the fast and slow motion of the moon in actual practice. The moon speeds up and slows down if you observe it over a period of time. And it speeds up much more than can be accounted for just and it's got some really crazy kind of movements that, as I read in the astronomy book last night, it's very, very complicated motion. In order to account for the speeding up and slowing down of the moon more precisely, then the Rambam mentions that there's a second circle that's going around with the moon. That's the second circle is this bicycle tire. Now, the point that I've been trying to make with all this kind of stuff with this bicycle tire is that if you were to watch the bicycle tire just from the very edge of the tire and not pay attention to the fact that it's going back and forth in and out from where you are, deep and shallow, but rather just pay attention to the motion sideways, you'll see that the motion follows that, and at the edges it is slowing. It is a slower motion than right at the center. The reason being that at the edges it's spending a lot of motion. Huh?
Spin it with the other hand.
What? Okay. Now I want to go a little bit slower so that you can get a better picture of it. Now let's. You're going to get all greasy. Don't answer
So just take your word for it.
All right. No, but the point is like this: when the moon is near here, a lot of the motion is spent going back and forth this way. You can't see that because you're so far away. You don't have depth perception. When it's going over here, all of its motion is sideways, so therefore it looks like it's going faster. So if it's going the same rate around the circle, if you look at it edge on, you'll see it's slow at the sides and faster at the center, slow at the sides and faster at the center. That is the picture of the moon, and then the moon, in addition to this, is going around the big circle. So since it's going around the big circle and it's going back and forth, when it goes back, it's going slower around the big circle. It's viewed going slower. When it's going forwards this way, it's viewed going faster. So that will account very closely for the actual path of the moon speeding up and slowing down.
Which means if we calculate the rotation,
Huh?
second rotation,
Yeah.
the second orbit, if we measure that, so then we have no problem with the speed.
No, you have no problem calculating because since all of these rotations, that's why I wear gloves this time. All of these rotations are circular rotations. And soy, and soy means it's a constant speed with a constant number of degrees per day or whatever. So then you can easily calculate where they are on these circles at any time. The complicated part, and that's what we're going to work on today, is then adding together making the corrections so that we see from our point of view, which is off center, and looking at two circles where the thing actually is, and that's what we're going to deal with today in the sheets. So now I'm going to proceed to those sheets, and also I'm sorry, I lied to you yet again. I have to mention one other motion of the moon, which I did not refer to previously, and it comes in later in the Rambam. I don't know if we'll be able to discuss it tonight, but just so that you have an understanding of what it is. Okay, you remember the other night when we had the demonstration of our guys walking around this circle here, and they went from 0 over here at chest height, went up here to summer, down to autumn, down to winter, back up. But the path that the sun follows in the sky is inclined at an angle of 23 degrees from the equator of the Earth as it's projected out into the sky. So there's this imaginary line inclined at 23 degrees. That's what gives us seasons. The summer is when the sun is very high. The autumn is when the sun is equal to the equator. Winter is when it's low and comes back up. This 23-degree angle is called in English the ecliptic. It's the path of the sun, Mahalach Hashemesh, through the sky. The moon basically follows this path of the sun, not the equator. Follows along the path of the sun, and it has an additional thing that goes above and below this path of the sun by about 5 degrees. So sometime during the month, it crosses the path of the sun, going north, and then later on, it crosses the path of the sun, going south.
So the circle is,
Huh?
so the circle is the opposite way of the.
It's a wavy.
Could you draw it on the board, maybe?
I will draw it in a second, but the point is like this. It's just, we had our guy going here like this, right? Up like that. The moon is going somewhere along here. At some point it goes up like this, a little bit higher. It can go up 5 degrees higher, so 23 and a half degrees where the sun is at the highest point. The moon could technically be 5 degrees higher than that, 28. At some point the moon will come down and go below it. So it sort of wiggles around above the thing. In the course of a month, it goes above the thing once and below the thing a second time. The time when it goes above, going north, when it crosses that path going north, is called the Rosh. And when it crosses the path going south, it's called the Zonov. And one can calculate the places where it crosses the path. It's not actually meeting the sun, unless the sun happens to be there. The sun could be somewhere else. It's crossing the path, going across the street. So when it goes north, it's called the Rosh, and when it goes south, it's called the Zonov. That's so it sort of like wiggles around this thing. Now, let's think, just an interesting point of view. Right now, we're getting close to the 1st of December. December 21st is the first day of winter. It's the lowest point where the sun is. So the sun is getting very, very far south. It's probably around 20 degrees south by now. If you have a full moon, the full moon is always on the opposite side of the sky from where the sun is, right? So therefore, the full moons during the winter are very far north. If you go outside tonight and look, we're a few days after the full moon, you'll see the moon is quite north. Likewise, in the summertime, you'll find full moons are at the south. It's just an interesting point to remember. But anyway, so the moon follows basically the sun's orbit. It's on around the same part of the circle, except it goes a little bit north and it goes a little bit south. The place where it goes north is called the Reish. The place where it goes south is called the Zonov. The Rab mentions this, and he says you can calculate where they are at any point in the month. But the funny thing about them is that this month's Rosh is over here. Next month's Rosh will be backwards over here. It moves backwards. The Rosh and the Zonov move backwards in time. Again, the same kind of thing. That they have a Mahalach and soy, so to speak. There's a rate given with it. There's a starting place of what the Rambam calls the Easter. And then for each day, you know what it is. You can figure out where the Rosh and the Zonov is at any time. Okay,
What date of the month does it go above?
It depends. It depends where it is. Okay. Now let's go into the sheets here. Does everybody have a copy? Huh? Here's copies. I made 25 copies. They're all stapled at the lower right-hand corner, which is totally the craziest thing I ever saw. But that's they have this fancy copy machine and staples. And Shmoy came to the sky. Here's the equator. This is on our shell of the sky. Then you have the ecliptic, which is at 23 degrees like this. And then you have the moon's path, which is something like this, which goes, let's say, goes north over here. And then it comes around back here, and then it goes south over here, and it comes around north again.
Isn't it a much smaller circle then?
No, this is on the whole. We're looking at this circle from inside when we're lying on our back and looking at the sky.
So the circle will be just as large as the sun.
Huh?
It would look like
So it'll look like it's just as large as the sun.
it wouldn't be
The
as
circle will
wide.
look
Same
just as
path
large
the sun.
as the sun.
Yeah, every circle here is what's called a great circle. Any circle that you make on a sphere that divides it in half is called a great circle. All great circles intersect each other at exactly 2 points. Most they're the same great circle. So you see, for instance, on a globe, you see these lines of longitude going this way. They all intersect here and here. They all intersect the equator here and here. Any circle that divides a sphere in half will have this characteristic. But anyway, these are great circles because they surround the Earth entirely and they divide it in half. But the ecliptic is inclined at 23 degrees, and the moon's orbit follows the ecliptic mostly, except it goes a little bit above and a little bit below.
It's 28 degrees off the.
All right, yeah, all right. Well, let's not spend any more time. Let's start getting to the Rambam, and we'll start at page 7. Okay, here's our famous picture. And you might not recognize this picture, but we saw it the other night. That's when we moved the observer out of the center of the circle, off the center of the circle. That's the sun. This is how we're now going to do the sun, which the Rambam does, starting with Yudal from Yud and all the calculations necessary to find the Makam Amiti of the sun. Makam and Soy of the sun is constant speed going around the circle that's inside here, right? This inner circle. The sun is going around, and it follows this. The observer is O, that's us on the face of the earth. And we are offset. We're not in the same place as the center of the circle around the sun is going. We measure degrees as if they are written on the outside of this big circle on the outside, which is centered around us. We are the observer, so we measure stuff on that according to that. All right, so now, the angle Gimel, you see I made little angles inside here. There's a little curved line that joins 2 lines, and then there's a letter associated with each of those things. And the right here explains what they are. Angle Gimel is what the Rambam calls Geva HaShemesh. That basically is the place where the person is situated, a line where the person is situated through the center of the sun's orbit. That's compared to the 0 mark. That's basically where it is. So if you remember when I was doing,
On the bike,
No, remember, forget that the bike is only dealing with the moon. Let's go back to the first demonstration where we had Rafali going around in a circle there. And then I said the way we make him be faster and slower is when I move off, the observer, move away from him, and I pushed him forward this way, and then his circle goes around me, from my point of view, goes faster and slower. I'm now pushed off the center. These things are this angle Gimel is the angle which determines how far, where I am standing at my center from him. You know, nobody understands this at all, do you?
What's G?
Huh?
What's G over here?
that's where the sun would be.
What's that other line? G.
What's G?
Angle Gimel is between the line that bisects the center and line G.
Angle Gimel, yeah. G is just the same direction as our 0 line. That's all, except it's on the sun's orbit. So now what happens is
What is the angle?
all right, what?
What are the measurements? Any angle? What do they give you? They don't give you a certain point. Why are you measuring angles?
Because that's all you can see in the sky. All right.
That's where the sun would be.
Huh?
I should ask a
What?
Is the sun's, what the sun's orbit is, or what the sun actually is?
No, all right, here, let's, what?
That's the opposite distance of what the sun is, what's closer to Earth.
Okay.
Place. Divine. Divine.
Okay. Now,
No violence.
the sun's, the inner circle goes around, hold on, but we had, so I don't hit your head. Okay, the inner circle goes around like this, okay? Sorry, going around like this, okay? Sorry. That's the inner circle, okay? Now, that is the sun's orbit, the Halach and Soy. It's easy to calculate that because it goes the same amount every day. We know where it started, we know how fast it's going, we know how many days go by, we know where it is.
We're the
Easy to
center.
calculate that. What?
We're the center of that.
Huh?
No,
No.
the sun is.
So
He's the center of that, okay? Now, you're coming over here, you're gonna be the guy who watches, okay? You stand right over there, okay? Okay, now that's 0.25, which is called Tkufa Shmuel in the Gemara. That difference is gone. The Rambam's number here, 59 minutes, 8 seconds, and actually 19.8 triplets, or whatever, shlishiyos. This number here, if you divide that into 360, you'll get a number of days for the year, which is almost identical with the correct, the most accurate number of days. So it's an amazing thing, how accurate the Rambam's movement of the sun is. But anyway, so the sun is moving 59 minutes a day. In 100 days, how far does it go? 98 degrees, right? It almost moves a degree a day. 98, 33, 53. How do you know where the sun is 100 days after the Iker? I have an example on page 7 in the center there. You add where it was, 7, 3, 32, add 98, 33, 53. So 32 plus 53 is 85, right? Except 85 is bigger than 60, so we carry one cheluk over to the top there, and we end up with 105, 37, 25. Easy to find where the makam and soya, the shemesh, is at any point in the future, because it's always moving at a constant speed. Everybody understand that?
Why adding 98?
Huh? What?
Why adding 98?
That's only the inside. We didn't get that meat.
No, that's right. Miti is where the fun begins. What'd you say? 98 is how far it moves in 100 days. Just an example for the addition. Goiva Shemesh. Where did it start? Goiva Shemesh is a particular angle, 86.45.8 at the Iker. After 100 days, what does the table say?
100 days is 98.
No, the Goiva Shemesh. Goiva Shemesh is on the left-hand side of page 7. After 100 days, it's 15 seconds. 15 seconds is a quarter of a chelek. So it's only moved a little tiny bit. It's almost the same. It's very, very slow. Those two numbers, Goiva Shemesh and Makam and Soy, are all you need to be able to figure out the Makam Amiti. All right, now let's go to page 8.
How do you do that? How do you figure out
Huh?
the
Let's go to page 8. We'll figure out how to do it. Basically, what you need to do is you need to add a correction to the Makam Hoim Soy. What? Page 7, that we calculated two things, the Goiva Shemesh and the Makam and Soy. Both of them are easy because they're both constant speed, constant rate. As a result, if you know how many days in advance, multiply it out, and then you get where you are. Okay, now let's read this little drasha that I wrote here when I was a foolish young man. All right, and observe the same picture basically. The observer is at O, in the center of that big circle, all right? He measures angles starting from E. That's Tlet. I measure my angles like this. I'm lying on my back with my 2 pencils attached to a protractor, measuring angles all night. Okay? I measure those angles starting from 0 over here.
So when you're lying on your back, where is 0?
Huh?
When you're lying on your back, where is 0?
If I'm lying on my back, if you show me that picture of the sky tonight, I can show you where 0 is. If I'm lying on my back, this is north. I'm lying on my back like this. Right up there is 0. I have a picture where the two things cross. That's right up there is 0. Except we're going to put it right over there because we're looking at everything from the top. Anyway, so we're lying on my back and there is 0. Okay? I measure where the shemesh is from the point of view of that. The small circle, remember, isn't measuring stuff the same way I am because I'm offset from the small circle. Remember that? So since I'm offset, my line of sight is going to cross in a different place than the center of the small circle does.
It's a small circle.
Huh? The small circle is the actual orbit of the sun. It's a small circle that moves at a constant speed. But we're off-centered from the small circle, so we see the sun moving faster and slower at different times of the day.
What's the big circle?
Huh?
The big circle is the world.
Huh?
The big circle is from your point of view.
Big circle is the sky, the sky that we see, and we have conveniently marked off little degree marks along the sky with a very long iridescent marker. Okay. So, so we're measuring these. We see those things on the sky from our point of view. As far as the sun's orbit is concerned, the sun's orbit is not centered around us. The sun's orbit is a little bit off from us. We have to translate our measurements of angles to what the sun's measurement of angles is as it goes around its circle. And they're not the same. You don't believe me, huh?
I believe it.
Remember when I had remember I had those two pencils there, and I had to take one step over here, and they were like this big of an angle, right? He took one step. And I had to take
It was
a
less of an
step
angle
over
than
there
the-
was less of an angle, right? Even though he took the same step. That's right, because I'm observing not from the center of his circle. His circle, all the steps are the same size. My circle, where I'm observing from, the steps look different size. So I have to translate to my measurements what his
You're gonna have to add
measurements are.
something.
Huh?
You're gonna have to add.
I have to add a correction.
Is the correction always the same correction?
No, the correction is in this
Depends how
table
far away
here
he is.
called Manas Hamaslo. Okay?
It's gonna depend how far away he is. Your correction will depend on how far away you are off
From
the
the
center,
zero, off the zero.
right?
Yes, exactly. And it depends on which part of the orbit it is. Because at certain points it's exactly the same. If the Shemesh is at the Goiva HaShemesh spot, then he's in a direct line with my center is in direct line with his center, and there's no correction. Right, so now, to translate the small circle angles to large circle angles, I'm reading what I wrote 15 years ago or something like that, we add or subtract a correction called Manas Hamaslu. All right? So what? Now here we go, the cookbook. Let's take the cookbook. Given Mokim, Shemesh, and Soy. We did that on page 7, right? Subtract the current value of Goiva HaShemesh. We did that on page 7. And you get what's called Masl HaShemesh. That's the difference between the two things. Masl is mem, angle mem there. It's between the Goiva and the Mokim and Soy. Then we go and look at our table here. And we look up the Manas HaMasl associated with that difference between those two things. It's very simple. Just look at the table. You add that or subtract it depending on what which side of the sun is, to the Makam Shemesh and Soy, and then you get Makam Shemesh Amiti. It's the correction. The Manas HaMasl is the correction for our off-centered observing point to the Makam Shemesh and Soy. That's all it is. It's a little small angle that you add or subtract, depending where it is, to be able to do it.
You're
What?
subtracting.
How does it work?
Huh?
I don't know which one. How do you?
I can show you that it's a long trigonometric derivation
No,
to get to
believe
these numbers. I'm not going to do that.
You're
Robin did
subtracting
that.
this.
What?
You're subtracting this from this.
What?
You're subtracting this
No.
from this,
I'm subtracting the actual Gaiva Shemesh, which we
which would be
calculated
one
here.
of these.
Which we actually, at the time that you want to see it, here's the Gaiva Shemesh, here's the Makam Shemesh and Soy.
So
Right?
you subtract Shemesh from the Makim
So
Shemesh.
subtract the current value of Goyim HaShemesh to get Masel HaShemesh. Masel is this little mem here. You see the little mem? That's the difference between... Huh? I'm sorry, what? Mem, yeah, it's a little guy there. Huh? Yeah, the little guy.
Between the mem and the gimel, that's what you're trying to find
Yeah.
out.
Yeah, it's just the mem. From his starting point up until where he is on his own orbit. That's Bays. That's both mem plus gimel is Bays.
Where's Beis?
Huh?
Based on site.
Bays is them soy, which you just know that's going around this one. Okay? The line between the observer and the center of the circle splits up Bays. Part of it is Goy Shemesh, and part of it is the what's called the Maslu. The Maslu is the only reason we calculate the Maslu is because we need it to look up this correction in the Maslu and Manas and Maslu table. That's how you do. Take our example, 100 days, okay? Just copy the values that we got the previous page. Shemesh. Where was the Shemesh Hamtsoy? 105, 37, 25. Right? Gaiva Shemesh then was 86, 45, 23. Subtract them. 25 minus 23 is 2. 37 minus 45, you have to borrow 60 halakim from the degrees column. And add to that, you get 97 minus 45 is 52. Then you have 104 left over, minus 86 is 18. So the Masel Shemesh is 1852, which is very close to 19. Let's look at our table.
1852, and then there was 2.
Yeah, but see, we just rounded up to 19 degrees. Okay.
Okay.
So we look in the table over here. 20 degrees is about 40. Okay.
What's the 340?
That's because that's if you go around the other side. If you go around the other side, it's the same for 340. Use the same correction. All right, now 19 is not in our table. 10 is in our table, and 20 is in our table. So we do is called interpolation. You know what that means? You figure out between those two which one should be.
Rounding.
That's not rounding. From 10, if it would be 10 degrees, it would be 20 halakim, right? If it's 20 degrees, it's 40 halakim. So how much is each degree? How many halakim is each degree between those two boundaries? 2. So therefore, we're at 19. So it's 40
38.
minus 2. It's 38. So 38 is the manas masl, and it's to be subtracted. So you subtract 38 halakim from our makam hashemesh and soy, 105, 37, 25, the bottom line of the page there, minus the 38 halakim gives you 104, 59, 25, which is now the makam shemesh hamiti.
Which is where you have to look to see this up.
Huh?
Which is where you look to see this up.
That's where you would see on your own measurements on the sky where the sun would be at that moment.
So you subtract it from the Makim Shemesh Hamtsoy, not from the 19, but from the Makim Shemesh Hamtsoy.
No, that is correct. This maslul thing is only there so that you can use it to look it up in this table. That's why it's there.
But this 104 is measured from 0,
Huh?
not from...
I'm sorry, what?
This is measured from 0, not from where...
That's correct.
Not from the other.
It's around here. Okay? All right.